magnetization and demagnetization. Then we'll focus more on artificial magnets. Then after dealing with artificial magnets, we can look at the applications. Applications of electromagnets. We can look at applications of electromagnets. Then if time permits, I'll talk about its magnetic field. Then after that, we look at the place So quickly, we'll look at the introduction to magnets and magnetic field. Then after that, we'll look at the types of magnets that we have. Then what are the terms you use when you are talking about magnets? Then after that, we'll look at the properties of a bar magnet. Because for physics class, the best for us to study is a bar magnet. Then from there, we look at how we can produce a magnet and how we can reduce magnetism or remove magnetism totally. Then, focusing on artificial magnets, we produce magnets ourselves artificially. Then, after we have produced it artificially, which is taking these two methods, then we look at the application, which is the one we would be dealing with, solenoid. A metal inside the coil wire, solenoid. Then, we look at Earth's magnetic field and elements of Earth's magnetic field. So, this is 5 minutes to 11. So let's start. There's nobody in this place that will say it that you have never seen a magnet before. If you have never seen a magnet before, you would have heard about it before. If you have a refrigerator at home, you would have seen a magnet. If you open your refrigerator, you'll see that you usually use force to open it. And when you are trying to close it, the fridge will drag, the door will drag itself, Abby, and you can feel that force. What is in play there is magnets. Same thing with this earphone you use, your earpiece. There's magnets inside. If you want to test it, you can take your earpiece. I don't know if there's anyone that has here. Let the earpiece face each other. You will see that they will attract. Take the lower part of the earpiece and the upper part, put them together, and you see that the upper part together, and you see that they will move away. They will repel. Why that is happening is because there's magnets inside your earpiece. And all of these magnets, they serve a specific function. So we want to see how they serve those functions and what do we even call the magnet itself, in case you have never seen. Now, one of the things you need to know is that this topic can be so abstract. It's a topic that your brain has to go with. It's not a topic that you will see what is happening, but you have to know what is happening. We're going to be doing a whole lot of left-hand rule, right-hand rule, corkscrew rule, a whole lot of rules. Then you also have to imagine a whole lot of things, because when I talk about Faraday's law, and I'm also talking about Lenz's law, I'm talking about back EMF, all of those things come from varieties of assumptions, and the assumptions cannot run on the board. And when we are talking about magnetism, another difficulty students used to have is because our class is two-dimensional. I can only go up and go to the side. That means I can go through y-axis, I can go through x-axis, but I can't come out of the board. So that will now be dependent on you to assume that I'm coming out of the board. It's another difficulties. So magnetism will be making use of 3 dimensions majorly. Coming out of the board, going inside the board, going up the board, going to the right of the board, going to the left of the board. All of those things are going to be imaginary. So you have to be ready for that. And you must pay close attention. Magnetism is very simple, but depending on how you also take it. So, but this is the easiest aspect before we get to where we are going to be using our dimensional approach. So when you're talking about magnetism, magnet was first discovered some years ago, I think in China, when during those old days, there were some people that the shoes they used to make is these days that we are making all these leather shoes. In those old days, they used to make wood. It is wood they used to make their shoes. Then those woods, we have nails. So one man come, they will nail it and they will make it in form of a shoe. All those farmer, all those sheep and goat rearers, they used to have it then. Then there was a day some of them were walking, going around, taking their animals around, and they noticed that when they try to take a step, it's becoming difficult to move their legs. Just like, you know, the shoe is made from nails that they've used to nail the woods all together. So while they were trying to move, they noticed something is pulling their legs. Just like the way your mom used to tell you when you were a child, that when you drop a food on the floor, the devil had eaten it. And again, from that moment, you thought that the devil lives under the ground. I think same scenario happened. So they thought about it, that what could be pulling our legs is so difficult. And if it is this generation, we might have done 7 days fasting and prayer. So at the end of the day, they discovered that black thing. And they realized that it is that black thing that is pulling their legs, pulling all the nails and the metals in their legs. And that black thing, they now took it home. I think you have watched the movie, maybe Gods Are Not to Blame or something. When someone dropped a bottle and the bottle became something like an idol. So when they saw the magnet to that black thing, the place where they saw it is called Magnesia. So when they saw that black thing, they thought about it, that what could this be? It looks like a mysterious thing, and they took it home. So they started keeping it very well, that it must be a god or one of those things. So when anybody is sick, they will take it and put it inside water and give the person to drink, and the person will be okay. Were you there? Were me there too? So I'm not saying that if you have malaria now, go and drop magnets inside water. So, but you know, sometimes your belief sometimes work with your, and a whole lot of times you may actually recover from some sickness naturally that you really did not know. But they might have felt that it was the magnet that was working. So until a scientist came and had to go and study that black thing. That black thing was called lodestone. And that lodestone is what today became a magnet. So magnets can be seen naturally, but it is not everything that you see that is a magnet. I can look at this iron now. This iron is not a magnet, but the iron can become magnetized, can attract a magnet, and can also be attracted by a magnet, which you might have witnessed before. So anything that has the ability to attract another thing is usually called a magnet, because it has, even without the earth itself, acts like a magnet. So all of us are attracted towards the surface of the earth one way or the other, not because we are metallic though. So the first thing we want to do is define. So what is a magnet? Right. A magnet is a substance. A magnet is a substance that has the ability. A magnet is a substance that has the ability to attract a magnetic material. To attract a magnetic material. So we're going to talk about your transformer works. All of these things are based on magnets. So we have two types of magnets. The two types of magnets are natural magnets and artificial magnets. Types of magnets. We have a lot to do. All these ones are just still play. So let's just write it short like that. So types of magnets. Natural magnets. You all know what natural magnets is. It is seen naturally, Abi. So we meet it on the earth. We didn't produce it. That's what the word natural magnet means. Why artificial magnets is usually produced, Abi? So the ones you produce yourself are called artificial magnets. Why the one you met on earth are called natural magnets. So they won't ask you to define that. So let's write example of natural magnets. Ores of iron. Examples of natural magnets. Just write natural magnets, e.g. ores of iron, like the magnetites, the lodestone, ametites. So lodestone is an example of natural magnets. So artificial magnets, there are a lot of them. All the ones you produce yourself are artificial magnets. So there is no particular example that I want to give you. So when you are talking about magnets, in what forms do magnets exist? Forms of magnets. Forms of magnets. All these are basic, so don't get too bothered. Forms of magnets. 1, bar magnets. Bar magnets. So this is a bar magnet. So it looks like a bar. It's the one we'll be using majorly. We'll use others too. So it has North Pole and it has South Pole. So this is called a bar magnet. Number 2, horseshoe magnet. Horseshoe, from the word horse. Horseshoe magnet. North, south. Number 3. Now, in this one that I want to write now, they are not necessarily magnets, but whenever current flows in wire, that wire will act like a magnet. We are going to see. There's just a wire, and the wire itself is acting like a magnet, all because current is flowing through it. I told you that a lot of things are imaginary here, so just hold on. That's why we'll take it step by step for you to understand. So, a straight wire carrying current can serve as a magnet. A straight wire carrying current. So the wire is carrying current. Just like this. So the current flowing upward or the current flowing downward. That can serve as a magnet too. Number 4, a solenoid. A solenoid. A solenoid. Solenoid is a coiled wire. So it looks like this. We are going to talk about it too. A solenoid. We'll coil that wire and we'll put a metal in between. Then we'll see some things. Then that can also act as a magnet. It can act as north, it can act as south, depending on how current flows inside. So a solenoid. The Earth itself, but we usually represent Earth with a uniform field, like this. Earth can act like a magnet too. So the Earth's uniform field. Are you there? So you have a solenoid, you have a bar magnet, you have an horseshoe magnet, you have the Earth acting like a magnet, and you have a wire that is carrying current acting like a magnet. So the major reason I have to say this is because I want to talk about some terms. So let's look at those terms one after the other. So when you're talking about magnetism, what are the terms you can hear? So number one, magnetic materials. Are you through with the board? Oh yeah, quickly write. We are going to, when we are through, we'll try to solve all of the questions, but please try to follow. We'll try to solve all the possible questions because magnetism can be somehow if you don't really have perfect understanding. So, but just pay attention so that you can solve those questions with me. I'll take my time to solve it. And I like the way we are doing this class. That's why you just have to pick your teachers and now probably just have a note for each teacher and use it like that. Maybe just small notes for each teacher. So that the problem we always have is whenever I'm teaching this magnetism, then we used to teach it at the latter part of the class. And by that time, we used to rush it. And questions do come out from here a whole lot. So, terms, magnetic material. So if I say magnetic material, you already know what that means. These are materials that can be attracted by a magnet. These are materials that can be attracted by a magnet. Shame in Oben today. Okay, there should be print to print their questions. And it's the same thing. You can confirm first. And they used to all fit from here. No, this metal. Let me show you. I should have been opening this. Sorry, we are coming.
Possible. Oh, both of them life. Precious. É sure. Yes. Danilo não.
So, I said these are my can be what? That can be attracted by a magnet. And most of the examples, iron, nickel, cobalt. Those are the major ones that serve as magnets. So they are magnetic material. Are you there?
Yes.
So you can say fenico or conifer or feconi. So Non-magnetic materials. Number 2, non-magnetic materials. These are materials without magnetic properties. These are materials without magnetic properties, which means they are not attracted nor repelled by a magnet. Materials that lack magnetic properties, e.g., tin. Àbí ṣágolo yín máa ń wà attracted, agolo rice yín. Tin. Gold. Does your gold feel attracted? Maybe to humans. Which other one? And zinc. Zinc is also an example. Aluminium. All those are examples of non-magnetic materials. Àwọn èyí tí magnet ò ní attract, they are the ones we are saying. So when you put magnets, they roll off. So they are non-magnetic materials. And what makes them a magnet, we're going to see. Number 3. Number 3. Yes. Magnetic field. So I'll be focusing, all of them have their magnetic field, but we'll see. Magnetic field. This is the region around a magnet. This is the region around a magnet where magnetic force is felt. This is the region around a magnet where magnetic force is felt. Please give me the phone. Let me share the link. Region around a magnet where magnetic force is felt. That's called magnetic field. I don't even know how to join. Sorry about that. We are trying to carry people at home along so that they can also, from the comfort of their home. Tó wù ẹ́ náà tó bá rówó next month sọ lè máa wò láti ilé. Èyí tó bá rí wò ń bẹ́ẹ̀ ni. So, but it's necessarily it can never be like your normal class. That's number what? Eh? That's what? Okay, I said the region around what? A magnet where magnetic force is felt. That is called magnetic field. So, e.g., something like this. If this is a bar magnet and it is north and south, the field runs from north to south. We are going to talk about it soon. Don't draw nonsense. So you will see where my arrows are facing. It matters. The arrows are going inside S, coming out of N. So it's important to know that. But I will still tell you about that, but I don't want you to write nonsense in your notes. So if I bring a metal and I place a metal here, this metal will not be attracted because it is not in the field. But the moment the metal enters here, then the metal will be attracted because it is in the field. So this metal will experience a force. All of those forces are what we are going to be talking about with time. So just take your time. So it's going to experience a force. That force can either be a pulled force or a repelling force, depending on what is inside the field. So, but let's move on. Next. Are you true? We are going to still draw magnetic field very well. Are you ready? Magnetic induction. Magnetic induction. Magnetic induction. That's number 4, Abby. Magnetic induction. This is the introduction of magnetic properties or magnetism. This is the introduction of magnetic properties or magnetism into a magnetic material. Into a magnetic material. When brought near a magnet, into a magnetic material, when brought near a magnet, when brought near a magnet. That is called magnetic induction. This is what I'm talking about. Let's say this is a magnet. It's naturally a magnet. All of you have experienced this before. Let's take a nail. When you bring this nail close to this magnet, they attract, Abby. So let's say the nail is here now. This attracts the nail. But one thing you will notice is that if you bring another nail, that nail will also be attracted without touching this one, just touching this alone. Then if I bring another one, it goes on like that, Abby. But as much as you are putting it, then it will start getting weak. So the farther it is, then the weaker it will become. We're still going to see. So, which means that when this metal touches this magnet, it becomes north. This becomes south. This will also becomes north. This will become south. This will become north. This will become south. We are going to see how that operates. So, this magnet has induced magnetism into the metal. And that simply means magnetic induction. When I make you to do what you will not do naturally, it means I've induced you. You know, when you are given, sometimes a woman might want to give birth, and you give an hormone, Abby, oxytocin, Abby, just to induce the labor, to make sure that the woman gives birth easily. Normally, the woman should be able to produce it herself, but just to make it come easily, then you can give such a woman such hormone. So it's the same thing here. This is actually not a magnet, it's just a metal. But bringing it close to a magnet, the magnet makes it to become a magnet too. And now imagine, the moment I break this one off, by the time I remove this, what do you think will happen to these ones? They will fall off. Abi, I hope you're following. They will fall off because the one that is strengthening them has been removed. Then everything will fall off again. And a lot of you that learn electronic engineering or all this, where do they use it again? Shoemakers. You have seen them pack a lot of nails around the giant magnets before. And all the people that want to screw, you know your screwdriver is not a magnet. But sometimes you use it to rub magnets. They use it to pick the screw. Then you tighten whatever you want to tighten. Have you seen that before? Yes. So all these are basic things. So it is by induction. And with time, it will become weakened. So number 5, magnetic sintering. Magnetic sintering. Like SINTERING. Magnetic sintering. This is the conversion of powdered magnets into a bar or solid magnet. This is the conversion of a powdered magnet into a bar or solid magnet. That is called magnetic sintering. Magnetic sintering. Are you there? So when you convert powdered magnets, so they can ask you in an exam, when you convert powdered magnets into a solid form, then we call it magnetic sintering. Is that taken? Number 6, magnetic shielding. Magnetic shielding. Magnetic shielding. This is the protection of the surrounding. Magnetic shielding. This is, how did I put the English before I change it? The protection of a surrounding from the influence of magnetic fields. The protection of a surrounding from the influence of magnetic field. And it is done by using a soft laminated iron core or ring. This is done by the use of a soft laminated iron ring. Iron ring. You don't use a solid, a bar magnet, you use a ring. Iron ring, soft laminated to prevent heating and all of those things. Iron ring. Now, let me move on from here first. When I talk about field lines, I'll bring you back again to that. But let me just show you. Let's say this is a bar magnet. This is north, this is south. This is another bar magnet. This is south, this is north. Now, the fields will run naturally like this, from north to south. But let's say I do not want these fields to run the way it is, like this. I can shield this environment from the word magnetic shielding. So I want to shield it from the magnetic field lines. So now what do? I will put a soft iron ring in between them, something like this. Then this is still my magnet. Now, as the field is coming, by the time it encounters this, it will go through that ring before it goes. So if you notice something, it will never pass through that center. It will be concentrated in that ring. All this center, there's no place that is free here. Everything, magnetic field, Abby. But in this place now, I've shielded this region. So any field that enters here goes round that place. Only this place is shielded from the magnetic field. Now, if I put anything here, let me just say I put a metal here. That metal will not experience any magnetic force. But if I put a metal here, it will experience magnetic force. It will be pulled or it will be sent away. But now, this place has been shielded, has been protected from magnetic effects. So that means that I've shielded that zone. Anything I put there does not experience magnetic field. Do you get that? So that environment has been shielded, and that happened because you used a ring like this. So that ring finds a way to concentrate the magnetic field and protect it from entering its middle. So just note that for now. I said it that if I explain this, some of you might be looking like, but you will get it. So let's move on. Please, do you understand shielding? Shielding just means you want to protect. So the question they can ask you here is that, how do you shield a magnetic field? What do you use? Answer me. When you hear magnetic sintering, what do you do? You convert powder to solid. I told you that some things are abstract. I can't really show you what is happening, but you have to try your best to understand it. So with time, you will get some other things, just as you are growing up in the subject. So please, just keep paying attention. I only explain it, but you can see the difference between these two and these two. This one shielded the center, Abi, and the field is not entering there. That's what we call magnetic shielding. But here it's not shielded, so the field can run through. Do you get that? So let's move on. The next thing to talk about, let's look at magnetic field patterns. Magnetic field pattern. Magnetic field pattern and properties of a magnetic field line. Magnetic field patterns and properties of a magnetic field lines. Now, you noticed I did something the other time. I took a bar magnet, north and south, and I did something like this. Now, if you take your bar magnets or any magnets, that region around the magnets, we call it the magnetic field. Abi? Now, this field, you don't really see them. You cannot see. I said something that most of these things are imaginary. You don't take a magnet now and say, oh, I can see all the field, all the region. But you notice something. If you take a metal and you bring it close to it, it's not touching it. You can take it further, you see that it's not attract. But the moment you are bringing it closer, it will attract. But without even touching the magnets. I hope you are listening to this. So which means that there is a region around that magnet that you cannot really see. That region is the field. But for us to see in physics class, we are going to represent it with all of these things. So how did I now know? It will always, the arrow will always be from north to south. How do I know? That's what we want to see. So they can ask you, so how do you determine magnetic field? So right, magnetic field pattern can be determined using one. Magnetic field patterns can be determined using one. Ion filings. Ion filings. Ion filings. 2. Compass needle. 1. Ion filings. 2. Compass needle. So, how do I use ion filings? There's a problem with ion filings. I might not be able to see the arrow. So, you take a cardboard. You take a magnet, the bar magnet, you place it under the cardboard. Now you place the cardboard on top. Then you take small ions. Please listen, oh, all these things will help us to know some properties. So all these small ions, we call it ion filings. Then you pour it on top of the cardboard. So when you pour it on top of the cardboard, you notice something. Then you start tapping the cardboard. I hope you're listening. When you start tapping the cardboard, you see the way these guys will be arranged. All of these guys will be like this. But that does not give me the arrow. That's what you will see. And you will notice something around this place. There will be a lot of them. That tells us something too, which I will tell you as we are moving on. You see a lot of them. So if you look at this pattern now, the pattern I've drawn here is what these ion filings bring out. So if I want, I can now take it out and just draw it out. Then you see that the lines move like this, the line moves like this, the line moves like this. It's the same thing I have here. So if they ask you, how can you draw a magnetic field pattern? The first way you can do it is by using ion filings. So how do you use ion filings? You use a cardboard and the bar magnets. So what do? You sprinkle the ion filings on top of the cardboard and you start tapping the cardboard and you see a particular arrangement. That arrangement shows you the magnetic field lines. So draw that. So we'll do the second one. Oh yeah. Please open your mind though. You can relate well with one of the easiest subjects to actually pass the most is physics. A lot of you used to be scared of physics because maybe it's because it's abstract. A lot of you used to be scared of chemistry too because it's abstract. And the easiest subject to fail the most is biology. Go and look at the overall highest in JAMB, top 10. Top 10 are engineering students. You barely see a biology student as top 10. If you see someone with 370 something, that person must have been an engineering student. But you can do it this time. If you go and notice most people's results, you will see someone having 98 in physics, 100 in chemistry, but the person will have like 78 in biology. A lot of you used to feel biology is the simplest because, yes, it's simple. You can relate. There are things you can really think about. If I'm talking about your heart now, your brain can start thinking about the heart. But if I'm talking about how this phone is working, except I bring out a whole lot of things that are working in the phone. That's how you will know. So at some level, you might start enjoying physics, but at some level, you might need to just follow. But funniest thing is that when you now solve questions in physics, you see that they are direct. Unlike biology, you can see all the options look the same and be like, more than mocking. That's why, and you can still come out of biology and feel like, oh, I will score 100. But you see results and you see 70 something, and you'll be surprised at what happened. You'll now be saying, even physics that I did not really do well, I did very well. Because when you get physics answer, you pick it, you know the answer. It's just like maths. When you solve maths, you get the answer, you pick it. You don't need to guess. You already know this is my answer, you pick it. Oh, more money. You don't know maths, you don't know maths. You know it, you know it. There's no magic. You try to solve it and you get your answer, you pick it. But biology, you can know it and get to options, and options will be confusing. So if you are not now calm, you will see some of the questions you will do today. So all I've just said here is that if they ask you, how can you draw the pattern for a magnetic field? You can use two methods, which is what? the use of iron filings, and the use of magnetic compass. So this is how we use filings. Just take your cardboard, put it on top of the magnet, then pour the iron particles, then start tapping. Then you will see this particular arrangement. That shows the magnetic field lines. So the next one, compass. This is what you do with compass. When I'm through with this, then I'll give you notes. Now, compass is just, a whole lot of you might have seen it before. It looks like this. It's used to show direction. Now, the red part there's a red part and there's a white part. The red part used to show the north and the white part used to show the south for a compass needle, if you have seen it in your lab before. Now, let's say this is the magnet and I want to draw the field. Then there's north here, then there's south here. You will now take this compass needle, you will place it somewhere, anywhere. When you place it, you notice something. This needle will rearrange itself in this format. You can see the way it moves. This black side is what? North. You will put a dot there, then you put a dot. You take it again, you place it here. From where you put that dot, you will realize it will move like this. This black part is still north, and this part is still south. You put dots there again, you do the next one. You take it again and place it, you will see that it will move like this. I'm making it big. So you notice something. This thing is, the north is here, pushing it away. Then that's the south. No, sorry. South should be attracted a bit. This side should be the north. The north will run away from north. Then let's do one more. So here now, I can have something like this too. So you can see the way the compass is moving. The north part is staying away from north, and the south part goes towards the north. Then it keeps moving like that towards south. If you do the same thing on the other side, you will take this compass too, you just place it. You just place it, you will notice something. Then it will go that same way too. Please just pay attention. I'll try my best to solve questions with you. Because that's the only way you can understand magnetism. So you can see the way it is. Moving away. The north part is moving away and the south part is staying. So that's how we determine the arrow. We now realize that the field always go from north to south. Then the arrow stays like that. So anytime you draw an arrow, so if I draw something like this, and I did not indicate anything here. This is A, this is B. Then my arrow is like this. From what I've drawn here, can you guess what A is? And B is what? You can see that that compass is always moving away from north and going towards south. So ordinarily, when you look at it, the arrow here is moving away from B. Now, moving away from B shows that this place must have been what? North. Moving into A shows that this place must have been south. It's one of the things the compass can tell you. So we will define it. So write this. Then let's define the magnetic field lines. Draw this one. Then we'll now draw all of the patterns for all the fields. So this is your compass needle. Are you ready? What's the use of a compass? To tell direction, to show direction. Please just calm down. No, we have not even started. All these are just beginning. There are a lot of imaginary things to do, and I'm trying to take my time. So please just calm down. You will understand everything if you open your mind, and you don't have a choice. You have to understand it. But it's abstract, so don't be discouraged. You will know it. Even in university, people have issues with magnetic fields and all. I remember I still had to organize a class to teach them on this aspect at the university, so it's not a problem. Are you true? So what is magnetic field lines? Don't be artistic. You can just use pencil or arrow. Just show arrow. Your own arrow can just mean that arrow, that part represents black. Artistic. Are you done? Okay, if you want to become a teacher, you can take your time to draw it. How many of you want to become teachers? It's not easy being a teacher. While standing here now, my brain is processing the best way you people can understand it. Even before I teach you, before I say anything out, my brain is thinking about, God, how would these people understand this? So my brain is working behind closed door that you cannot see. So it follows a pattern. Are you true?
Yes.
Magnetic field line is defined. Magnetic field line is defined as an imaginary line of force. Magnetic field line is defined as an imaginary line of force around a magnet through which the north pole of a magnetic compass. It's an imaginary line of force around a magnet through which the north pole of a magnetic compass tends to move. Everybody look up. Between the north and south pole, which one is moving away? The north. So the direction in which that north pole tends to move is what gives you the magnetic field line. Is that taken? So this is a magnetic field line now. It's a magnetic field line. The line runs from north to south. So the next thing is, right, the force due to these magnetic field lines, you need to note that part. The force due to this magnetic field line is usually taken, the force due to this magnetic field lines is usually taken as a tangent to the field. Tangents. You know how to spell tangents now when you have a circle. So let's say this is the field lines. This is what I'm saying there. Please don't get tired though, or you will leave another day to do it. You are tired. What? Tired in what way? When is your break supposed to be? Eh? Eh? Talk, let me hear you. You did not sleep overnight because of tests. So you have been sleeping before. Wow. So you people have been sleeping before. So what now makes yesterday different? You did extra. So if I give you test questions now, will you not sleep off? They are printing test questions. While we are waiting, I'll give you like 10-30 minutes to relax. Find something to eat. Then when you're about to start, then I'll call you inside. So let's just, don't worry, I will just send it. All these parts are still understandable. So please, let's just do a little more. I will soon give you a break when they are done printing the questions. Ẹjọ́ tó máa ti print questions tán, they should let you know so that before they come, they can have 30 minutes break. We will still do the correction of the questions though. Yes, and we might do it in batches. So yeah, please, let's just pay attention. Be strong, be strong, be strong. Do you want to stand up? So please listen. Imagine, these are called the field lines. Please pay attention. These are called the field lines. Now, if I say you should determine the direction an object will go if placed at that point, you are going to draw a tangent to that line. That tangent tells you the direction of force. So if they ask you, the direction of force on a magnetic field line is determined by what? Is determined by a tangent to the field. Do you get that? That's just a simple statement you need to note for now. Now, let's now draw the patterns before I talk about the properties. Magnetic field patterns. For like poles and unlike poles. If I have a bar magnet, this is north and this is south, and I bring another bar magnet close to it, this is south like poles, this is north, this is south. Normally the field always run from north to south, Abi. As the field is coming out that it wants to, because of this one, they will repel, and you have something like that. So it will never run like this, no. Because of this north, this one is coming this way, this one is also coming this way. So when they meet, they repel, they don't cross. That's why when I start giving you the properties, you will see. So they go this way. So at this region now, if I put anything here, do you think that anything I put here, do you think it will experience a magnetic force? No. So that part where you will not experience a magnetic force is called the neutral point. So N sub P is called neutral point. So there will be no magnetic force in that region. If you have south, look at the way my arrows are. Been watching them. Don't put another thing in your own notes. Let's say this is what I have now. South, south. What will happen? They will also repel, Abi. So the field will look like this too. But how will I know this place is south and this place is south? My arrow must have told me. Can you see that? You see the arrows for this one, they are going outside. Abi, for north, they go outside. For south, they go what? Inside. So this part will be your neutral point. Those are like poles. Same poles. South, south, north, north. For unlike poles, it can either look like this. After I've given you the properties, I will stop. I want to study medicine. I want to study medicine. Ayé ẹlẹ́nu. So do you think around this guy in the field, do you think there will be a region of neutral points? Is there neutral points here? Eh? Are you sure? There will be no neutral. I just drew field. The point, it might be like this. So it will occupy everywhere. Sure, you understand? So, but we cannot be drawing a whole lot. So because there is nothing repelling, everything is leaving north and they are going into south. So as they are leaving north, so they can live here, live here, live here. So they will occupy everywhere. Do you understand that? But here now, they are repelling. And that's why that space was left for it. Wow. I don't know. You can ask them. Maybe it's the toner or the drum. I want to know. You people are part of the problems. Please, maybe you are just joining. Please, you pay 200 naira for your tests every Friday. And there is nothing that says that you shouldn't have paid it latest Wednesday. Latest Wednesday. So that your questions can be printed on Thursday. And you come in the morning. You are not only the problem, teachers are part of the problems too. Because a teacher just sent some questions around 8 this morning. And we have to compile all those things. Immediately I finished teaching you on Monday, I compiled my own questions on that topic. Immediately I finished biology. Which day did I teach that biology? I also compiled the questions. So it's just like that. And there are a lot of tools now that we can use to make it easier. So, but if you have paid your money on Wednesday, then by Thursday they will print. They already know the people. But some of you just came this morning to write names. tó bá jẹ́ bí WAEC ṣe nìyẹn tó yẹ pọ́jọ́ tó sanwó náà máa print questions ẹ̀ wàá mọ̀ bóyá o máa lè ṣe exam. So there are challenges. So you would have, now there is light now, paper náà ti ń ṣe rubbish, òun náà ti ń go blank and all. So those are the things. So ẹ̀yin ọmọ ẹlẹ́gbẹ́ tẹ́ wà kíláàsì mo gbé bọ́m̀bọ̀m fún yín, but ẹ máa ṣe léni whether you like it or not. You will do it today. When I give you break now, I will go and look into it. So you can also have it like this. Do you think I will have a neutral point here? Because it will run from north to south. So gbogbo ẹ̀ ló máa block. This one can also run like this. You don't really need all those ones. Your brain should tell you that you have it. But I'm just indicating one or two. How will this arrow be? Will it be to the left or to the right? The arrows for this one should be to the left. Do you understand that? So it's running from north to south because north and south are close there. That's why. So yeah, let's look at the properties. From what we have said so far now, you should be able to note the properties. Are you through with the board? I'm always ready for the war again. Go down the road again. It's all this. Are you done? You are not right. You are not right. When you do like this, it means no, I am not. That's the best answer. Are you not writing? Yes, I am. I am writing. No, I am not. I am not writing. So if you do like this, that means you are not writing. That's what you just said. Can we move on? I want to want the printer. Have we really found a place where I call home? Please, so when I start solving questions with you, I'll be calling you one by one to explain. Because this aspect requires understanding. It requires your ability to express yourself. If you can't express yourself, you can't solve it. Because by the time they tell you that there is one paper that is placed somewhere and the current was going up this way, in what direction with a pin that is placed here, in what direction will it move? There's nothing to cram. You just have to analyze it and get your answer. So just be following step by step the way we are doing it. So can we move on? So properties of magnetic field lines. So what are the properties? Number one, it runs from north to south, like the properties of magnetic field lines. I already gave you the definition that it's an imaginary line, Abi. So it runs from north to south outside the magnets. It runs from north to south outside the magnets and south to north inside the magnet. It runs from north to south outside the magnets and from south to north inside the magnet to form a closed loop. To form a closed loop. It runs from north to south outside the magnet and inside, and from south to north inside the magnet to form what? A closed loop. This is what I'm saying. This is north, this is south, Abi. So the field runs from north to south. But within this magnet, you know, this is outside. But within the magnet, it continues. So it runs from south to north. You can see, let's say this one is coming this way. Then inside, it will continue this way. Do you see that? So if this one is coming this way, then it can go like this and come this way. So you can see that that's like a closed loop. Abi, that's what we are saying. So outside the magnet, it goes from north to south. Inside the magnet, it goes from south. So you can see the arrow inside. It's going away from south, going towards north. But outside, it's going away from north towards south. Please note that. Is that taken? So it runs from north to south outside the magnet, then south to north within the magnet, forming what? A closed loop. Number two. So when you are talking about a bar magnet, like poles repel, like poles repel, and unlike poles attracts for a magnet. Like poles repel, unlike poles attracts. You already know what that means. If I bring knots close to another knot, then what will happen? They try to stay away from each other as much as possible. Check that with your telephone earpiece. When I bring south close to south, they also do what? They stay away from each other. They repel. So like poles will repel. But if I bring north and south together, what will happen? They will attract. So unlike poles attract, like poles repel. We say poles when we're talking about magnets. Why we say charges when we're talking about electricity. So number three. Field lines do not cross. Field lines do not cross. How does it even want to cross? It's going from north to south, then back to north. So it's a circular thing. And if you bring them close together here, from that field, they will repel. So they will not cross each other. Field lines do not cross. Is that taken? Everything we have in this is one. Have you seen that I drew one on top of the other? No. This one, when I've not said anything. Right. The strength of the magnets is strongest at the pole. The strength of the magnets is strongest at the pole. Is strongest at the pole. You remember when I drew it the other time? I said something like, if I pour iron filings, I said there will be a lot of them around here. That shows that it is stronger there. And if you check this one, you see that there will be a lot of lines. So where the lines are concentrated, it shows that it's stronger. So the magnetic strength is always stronger at the poles. Do you get that? So they can ask you that too. So right. The more concentrated, that's number 5. The more concentrated the magnetic field lines, the strength is the same for every line, but the more it is together, the stronger it is. The more concentrated the magnetic field lines, the stronger the region of the magnetic field. The more concentrated the magnetic field lines, the stronger the region of the magnetic field. The stronger the region of the magnetic field. What do I mean by that? If I draw something like this, and I ask you that in what space, let's say A, B, C, and D, at what region do you think the field will be stronger? At D, where they are packed together. Or you have the field lines like this, and you have just few field lines. Between A and B, even if each line has equal strength, between A and B, which one do you think the magnetic field will be stronger? A. All of these things, we'll be applying them when you start talking about the applications proper. When I start talking about Faraday's law of electromagnetic induction, we'll be applying them. So please, we have not started. All these ones we are doing, they are still play. So pay attention. Because I can tell you that something is entering a loop, and something is entering a loop, and all of those things. What will be the effect here will be different from what will be the effect here. And you have to understand that. I said the more concentrated the magnetic field lines, the stronger is what? The magnetic field. So, number 4. A uniform magnetic field, the fields are equally spaced The fields are equally spaced with equal strengths at every region. The fields are equally spaced with equal strength at every region. And this is opposite for a non-uniform magnetic field. And this is opposite for a non-uniform magnetic field, so that I will not waste time on that. And this is opposite for a non-uniform magnetic field. So what am I saying here? If they tell you that there's a uniform magnetic field, just make sure that the field lines, my hand might not be up to scale now, but just understand what I'm trying to say. When you see that the space between them is equal and they go the same direction, like parallel, like that, then you say that the field is, the word uniform means it looks alike. So this is a uniform field. But if one is going like this, one is going like this, one is going like this, this field is not uniform. That means that the strength here will be different from the strength here. But for this one, the strength here is the same thing as the strength here, and it's the same thing as the strength here. Such field is called a uniform field. When the field lines are equally spaced and are going in the same parallel direction. But when they come together, then the strength here will be different from here, from here, from here. And we already said something that where the fields are more concentrated, that is when it is what? The strongest. Do you get that? They can just draw something like this and put all the options and say you should pick where the field is the strongest. It's as simple as that. It's not always so hard. Let's move on. So you can draw the two. So the first one represents what type of field? A uniform field. This one represents what? Let me borrow the word of P factorial. Kò lọ far rárá. Ṣó lọ far? Kò lọ far. Ojú ló mọ ohun tó yónú. Don't worry, you will understand it. It's just imaginary. Because imagine someone just drawing line and they say I should be drawing the line. Does that make sense? They are true. Oh, they are almost true. So are you okay now? Please, I begged you from the beginning that this topic can be stressful. It will stress you. But it's very interesting when you know it. It's very interesting. And we have not even gotten to where it is interesting. All these ones are just background knowledge for the things we need. Most times they might not even ask you questions here. We have not started. This is just introduction. So, and we can take our time. We will solve all of those questions in LAMLAD. We'll try to solve all of those questions in Remix, everything together. So when we practice them together, then you see that you will have no problem. Just for you to go and be practicing. That's what I'll take my time for, even if it is for us to come on a particular Saturday and come and do everything from morning till night, so that you will not have problems. Because now, right, number what? Magnets always exist as a dipole. A magnet always exists as a dipole. Dipole, D-I-P-O-L-E, dipole. There's nothing like monopole in magnets. In electricity, you can have positive, you can have negative. But in magnets, the smallest magnets still contains north and south. You can't separate them. And that is what we mean by the word dipole. That means that your magnet will always have north, irrespective of how small it is. So, for example, Let's say I take a bar magnet like this. This is north, this is south. When I break this magnet into two, to give me two more magnets, the two other magnets will produce its own north and south. This will also have its own either way, north and south. If you break this one again, it will still give you north and south, north and south. Do you get that? So irrespective of how far you break it, you will always have north and south. So if you break it to the smallest piece, that north and south can never be separated. And that's what we mean by the word dipole. Shoye, so a magnet always exists as what? Dipole. The north and south can never be separated. Are you there? Let me give you one more. Or is that enough? What if there's nothing to give again? And please don't forget that it is imaginary. Don't forget. And it's always moving in the direction in north of the compass we move. So now that you know about this, then, and you know this, then let's talk about this. Oh yeah, the time is what? You people better not be lazy, especially those of you that want to go to any field. I still understand some fields can be a bit, there's no field that there's no shege. There's no field. But I understand that some fields might be more demanding. They might be really, really demanding. Those engineering courses can be demanding. Medicine will take your entire time. Entire time is demanding. So all these 400 level medicine students now, during December, Christmas, no break. New Year, no break. They were there in the hospital. They were there in UCH. So there is no, at a stage, you will not have break again at all. No break. Maybe first or second year. Although, I think we have one of our students around too, Islamia. She has been on break. And she said her break is almost like 1 year. So she's in 400 level OAU medicine. I don't know one thing, OAU medicine these days, even Benjamin too, he said he will have a very long break this time. Maybe around August he will be around. So he will have like 4 or 5 months break. But I've not seen UI medicine break. Since I've been saying it. I know you used to be that stressful, but most of our students, them, this Michael, Elemi, all of them now they have resumed. They have started working. People in 300, 400 level too, they have started working. So, but there's a stage that you will be free at a time. And funniest thing is in 200 level, you are not going to do anything. You just go for classes. You will not write exam. In 300 level, you will not do anything. You will not go for classes. You will just be preparing for exam. You use like 1 year to prepare for exam. Let's just see how the experience goes. So, but the most important thing is that you won't have time. You might be in class from morning till night, and everything you did till that night, you must still read it overnight. I must still write up some things. So if you are lazy now and one work for exam from coffee, what you call coffee medicine, don't worry, you build your strength. Even if you are lazy now, you will build your strength with time. So don't be feeling like you can't do it. You can do it. Just build your strength with time. So it starts from here. When you get to campus, you see medicine students, the way they are reading. You see them. You have some of them as your roommates. You see the way they are reading. I be like, Shogunlaye. That's why if they paste results like this, you see medical students, 98A, 90-something A. There was one of the students that when we finished the exam last semester, I'm sure that this person will have A in all of the courses. I'm 100% certain. But this person after exam was still crying. Was still saying that, Dr. Sodium, I'm not happy. I'm not doing. I said, what happened? He said, the one I did last, I don't think I can have 90 plus. I said, shebi 70s, eh? Why do you need 90 plus? And she really meant it. That I have to be encouraging her and be telling her that don't worry, everything will come out as 90 plus. But if it did not come out as 90, just know that the world has not ended. I had to be sermonizing her. She said, but I promised, I said I must have 90 plus in all my courses. Yes, that's the mentality of those people. So it's not just to have A, they want to score everything. You can imagine out of 40 questions, someone miss one question and the person is crying. He wanted that 15. He wanted that 15 over 40. They say, okay. That's just how it is. When I was in OAU2, we had the same experience. You will just get to the board like this, you see someone score 40. But when I get back to the room, I'll see some of my roommates, especially Tafa, half a kilogram, almost 20. My party will be like, 20 over 40. Whereas èèyàn ní 39 over 40 á dẹ̀ máa sunkún. So, but it all depends on how you understand life. At a stage, you realize that some things do not really matter, but it is important. It is important. You will see a lot of that in medicine also. Some of you that used to feel lazy, you will get used to it. Ṣẹ́ni tó ti fail JAMB bí ẹ̀ márùn-ún kó tó ládmission tó jẹ́ pé gbogbo orí ẹ̀gọ́ ti ń gbóná. Ìwé òjò wọn lójúmọ́, get there, you see them. Thank God Ibe can share experience, Seun can share experience. Those are people that are already in UI. So they just decide to come back for one reason or the other. So they can tell you the experience of how it goes. You see people reading 247. Wanted to myself, I have not read anything. So please, you can go on break. So by 1 o'clock, you will start your mock. So you have 30 minutes break. You have your tests. So we'll continue from there in my next physics class. Please, make sure you do not forget what I've talked about today as much as possible. We'll be building on it. Thank you.